So I'm going to tell you a little bit about our work on precision timekeeping, so using specifically optical atomic clocks to kind of test fundamental physics, but especially we're focused on exploring the interface between relativity and quantum mechanics. So first of all, I want to say this is kind of a collaboration, and so there's, along with me, there's 3 other co-PIs, including Jun Yi, who's the lead PI on this effort, also Anna Maria Ray, also at JILA, along with June, and Igor Pekovsky, who's here. He's from Stevens Institute of Technology. And then there's a large experimental team, all listed over there on the left-hand side. And of course, again, want to thank our funders. I wasn't sure whether I should be thanking everybody or just the 2, so I listed all 4, but then put a little box around the 2 people who are actually giving us the money. Okay, and then the other thing I want to mention quickly is that in addition to Igor, who's here, and myself, we also have some of the postdocs who are doing the work on this effort with us, and I encourage you to talk to them. And Anjun has a poster, so I encourage you to check out his poster as well. Okay, so this is again shifting gears. We've heard about axions, we heard about EDMs, now we heard about charge neutrality. So this is another way to test fundamental physics on the tabletop, and specifically, we want to test relativity in the lab. And so first of all, I want to try to motivate why is that an interesting thing to do at all, right? And from my perspective, the reason that this is really interesting is we have these 2 phenomenally successful theories. We have the theory of general relativity, and we can now with LIGO, which is one of the most amazing, I think, developments in my lifetime for sure, see these cataclysmic events where black holes that have 10 to 100 masses of the sun, spin around each other at close to the speed of light and then merge, and yet everything that LIGO detects is consistent with the predictions of GR, in these kind of just these events that release more energy than we can ever comprehend. And at the same time, in the lab, we can do these amazing quantum science experiments with atoms and molecules that we've been hearing about, and everything's consistent with quantum mechanics, right? And yet, we don't have a quantum theory of gravity. We have these kind of contradictions when we try to make one. And so we're left in this kind of funny situation where we have these 2 incredibly successful theories. We can't find violations of either of them, but we don't know how to combine them. And so from my perspective, that both motivates testing both of these theories at, in different regimes and new regimes on their own, but also trying to find experiments we can do where maybe both of them are relevant at the same time and see how they interact with each other, see if we can see any hints of things not behaving the way we would naively expect. So if we want to test relativity in the lab, I would say if you want to test general relativity specifically, there's really only one effect that we easily have access to from GR that's sort of non-Newtonian, and that's the gravitational redshift. And I'm sure you're all familiar with it, but the idea is that if I have 2 clocks and I lift one clock up with respect to Earth's gravity, that clock will tick faster than an otherwise identical lower clock. And that effect to lowest order just scales with the acceleration due to gravity at the surface of the Earth, little g, the height difference between the clocks, and then divided by c squared. And so that works out very nicely if you just plug in the numbers. At 1 meter, you have almost exactly an effect of 1 times 10 to the minus 16 fractional change in the rate that these 2 clocks are ticking. So it's a small effect, but it's a real effect. We heard from Giorgio, I get to benefit from all the talks that came before, about Mossbauer spectroscopy yesterday, and about the Pound-Rebka experiment. And this was the first experimental observation of this effect of the gravitational redshift and gravitational time dilation. And as I said, it's a small effect, so to make it as big as possible, they put their source and absorber 22 meters apart in a tower at Harvard. And that gives you, because it's just 2 times, it's 20 times this 10 to the minus 16, you get an effect of 2 times 10 to the minus 15. And as we heard from Giorgio, these iron Mossbauer lines are narrow enough, have a high enough Q that you can actually resolve that. But I showed on the previous slide kind of doing these experiments with clocks, and Mossbauer emitters they're kind of like clocks, but you don't actually know what rates they're ticking at, right? So you might ask, well, why not actually do this experiment with clocks? The answer was at the time, you didn't have a clock that was good enough to see these kinds of very small effects. But clocks, atomic clocks have gotten good very fast. This is my kind of requisite, slide on atomic clocks, but I'm not really going to go into it. If people have questions, you feel free to ask, but I think I'm going to assume you all kind of know how atomic clocks work. And they've gotten better very, very fast since they were first introduced. So if you look at around 1962, 1963, when Mossbauer, when Pound and Rebka were doing their experiments with Mossbauer, you can see that the clocks weren't nearly good enough to see an effect at the 10 to the minus 15 level. But now clocks have continued to improve kind of at like a kind of Moore's law-like scaling exponentially. And as a result, now we can see effects at the 10 to the minus 18 level. This corresponds to these clocks being precise and accurate to 1 second or better than 1 second in 14 billion years, which is really remarkable. And that means that we're now at the level where we can even see redshifts, gravitational redshifts at the centimeter scale. This is actually a problem for clocks now, because if you want to compare clocks that are far apart from each other, you have to know their relative heights with respect to Earth's equipotential at the centimeter or better scale. And it turns out we don't really have a way to do that for clocks that are in different standards institutes hundreds of kilometers apart. But that actually means these clocks are actually the best way to make those measurements now. And that's given birth to this whole new field of what's called relativistic geodesy. What I'm going to say is that we're really interested in trying to probe these effects at even smaller scales, where we can imagine also putting these atoms not just in an internal superposition as we do to make a clock, but in an external superposition as we just heard about from Jason, atom interferometry basically, and probing what happens, and I'll get into this a little bit more a little later in the talk, but what happens when an atom is experiencing kind of a superposition of different proper times. And so I'm going to kind of arbitrarily say, let's say we want to do that at about the 100 micron scale, where, for example, Holger Mueller's group is now doing trapped lattice atom interferometry at the sort of tens of micron scale. So it's kind of reasonable to imagine doing these kinds of experiments. What does it take to actually get our clocks down to the 10 to the minus 20 level, given that they were at the 10 to the minus, that in, say, around 2020, or even still currently, they're at about the 10 to the minus 18 level, okay? So this is the clocks that both June and I work with. The systems are made on strontium-87, the exact same atom we just heard about from Jason. We use a rack, in my lab, we use a rack-mounted 12 centimeter ULE cavity as our local oscillator to probe this very sensitive clock transition. We put the atoms in this magic wavelength optical lattice to sort of isolate from their external degrees of freedom so that we're really able to take full advantage of this narrow line width, 1 millihertz line width clock transition. If you do that and you try to make a normal clock, you get pretty good performance. This is not record setting or anything, but it's a pretty remarkable clock, 6 times 10 minus 15 per root hertz, okay? But then if I just told you you want to get to 10 to the minus 20 and you plug in the numbers, it would take you 11,000 years to average down to 10 to the minus 20. So that's just not nearly good enough. Fortunately, there's kind of a hack or a trick that we can do, and it's exactly the same trick that Jason just introduced with this idea of gradiometry, basically. Rather than running one clock, we run two clocks. We break our atoms up into two ensembles inside of the same lattice, and they experience the same laser noise, the same local oscillator noise. That stability I showed you on the previous slide was limited entirely by the local oscillator, basically. And so by doing this, now these two clouds of atoms experience the same local oscillator noise. It becomes common mode, and we can cancel it out. And we can get much longer coherence times, not be limited by this noise, and get back to the QPN limit, the quantum projection noise limit. And now we can do orders of magnitude better in terms of stability. And then the amount of averaging time it takes to get to some number scales with that stability squared. So we go from 11,000 years to something like 6 days to average down to 10 to the minus 20. And June has been working along similar lines, has demonstrated even better stabilities. Just because we're at the QPN limit, this really corresponds to just having more atoms in the lattice. And now he's able to average down, as you can see, to below 10 to the minus 20 level frequency differences between doing measurements of a single ensemble and imaging it with a camera so that they can do comparisons between two halves of that ensemble. So this is measuring frequency differences between the top and bottom half of one spatially extended ensemble at the 10 to the minus 20 or better level. So with that, we're actually able to measure the redshift at the millimeter scale. This was demonstrated both in my lab and June's lab. And that then leads us to say, okay, now that we can measure these effects on these tiny scales, what can we actually probe in terms of exploring the interface between relativity and quantum mechanics? And one other point I want to make is actually already, even in those measurements, you had to worry about things like the atoms not being in one specific place, one well-defined place. It turns out in June's experiments, because they're operating in a shallow vertical lattice, the wave functions of the atoms are described by what are called Wannier-Stark states. And you can see that at the depths that they're operating at, there's some little probability that the atom is actually also on the neighboring site rather than the site that it's kind of mostly localized on. And if you have two atoms sitting on neighboring sites, they actually start to interact with each other. But because they're mostly sitting on different sites, they experience different clock laser phases, and that makes them distinguishable and actually changes the nature of their interaction. So Anna Maria and June did very careful work to really understand this physics and to figure out that there's actually kind of a magic depth of the lattice where these two effects cancel each other out and you can suppress density shifts. And that was actually critical for doing this very precise measurement of the redshift at the sub-millimeter scale and getting down to this below 10 to the minus 20 level. And you can start to see that this is now starting to deal with both effects of gravity, not really yet here in this context the effects of relativity, but the effects of gravity combined with kind of quantum mechanics. And so enter Igor Pekovsky and the kind of experiments he's been thinking of. And so what he's been thinking about is what are the experimental evidence for how gravity and quantum mechanics can really interact with each other. And we just heard about atom interferometry, where atoms are in matter wave superpositions and they acquire a gravitational phase. And then I just told you about time dilation, redshift experiments. And so in 2011, Igor and collaborators proposed a combination of those two, where you take an atom, you put it in a clock superposition, and then you send it through one of these matter wave interferometers so that it experiences also two different heights at the same time and has a redshift between those two paths. And that's to sort of somehow give you which path information about where the atom went. And as a result, you would expect to actually see that for certain interrogation times, you won't get a matter wave interference fringe anymore when you try to recombine them, because the atoms have kind of learned from the redshift which path they took. And so we're really thinking about how can we bring this kind of thought experiment to reality, and how to understand the consequences. And so with Igor, we've been, and the rest of the collaborators, we've really been thinking about what would this experiment mean? What is it actually testing? And it's really testing a regime where you're asking, is the t that you write down there, is it actually sort of a quantum operator t? And does that correspond to the proper time that it experiences, right? Should you put a little hat on top of the t or not? Now, Ron Fullman, who's also here, and I think we'll hear about this later today, did a beautiful experiment where he simulated this effect not with the redshift, but with a magnetic field, and indeed showed the results you would expect with a magnetic field. And so we're working on trying to actually see this from relativity, but it's very difficult. It requires a clock interferometry with a 1 meter superposition for strontium, let's say, and 10-second interrogation time. And that's just not something we can do yet in the lab. So what we've been working on under this effort is to think about new ways to test this. And in particular, are there ways to actually do it at smaller separations where we can already do that, where June is already starting to see some of the effects of being in a kind of spatial superposition. And then I'll say that Igor's also working with other collaborators on using other techniques, other systems basically, to maybe test some of the same physics and to understand it. So if you want to test this in one of these Wannier Stark lattices, one of these shallow lattices where the atoms can actually be put in superpositions of being on different sites, we've now understood that you don't do exactly the same test where the degrees of freedoms become entangled with each other, but you can test this question of maybe what we've been seeing when we measure the redshift is that the atoms are just sensitive to the expectation value of their kind of proper time that they experience. So maybe you really can't be in a superposition of proper times, but you just kind of experience the average proper time, okay? And what Igor and Konstantin, who's the postdoc who's here at the meeting, have kind of realized is that there is a protocol you can use, I'm not going to go into details, that kind of involves doing a sort of echo-like flip of the states of the atom halfway through, where even for a very small height separation, you'd be able to see a clock shift that's of the scale that we can actually measure. So in particular, for a millimeter scale height shift, you'd only need to see a 10 to the minus 19 level clock shift. And these are the kind of shifts that we are now able to measure and able to resolve. So these are the kind of experiments that we're actually really working towards. Igor and Konstantin and me are also thinking about, are there other ways that we can use these systems to maybe test relativity? I think later today we'll hear a lot about ideas of trying to measure gravitationally induced entanglement by putting large masses in macroscopic superpositions. And what we've been thinking about is now that you have these kind of systems like the thorium nuclear clock, and even to some extent the systems that Giorgio was telling us about with higher energy Mossbauer transitions, you can imagine maybe using those to source gravity. Because when you when you excite a thorium nucleus from the ground state to the excited state, you're of course changing its mass. And we're now entering the regime where we can do coherent superpositions. We're just starting to take baby steps towards being able to create coherent superpositions of these different nuclear states. And if you had enough of these things, you would actually be generating a superposition of mass that you could coherently control and maybe use to source superpositions of mass. So this is very optimistic and forward-looking, but these are the kind of things that we're starting to become possible that we're very excited about. Anna Maria's group is thinking along related but somewhat complementary lines, where they're really thinking about how these effects enter into many-body quantum physics. And in particular, they like to think about this redshift in terms of thinking about it as a mass defect. Like I just said, if you have a higher energy, it's equivalent to the atom having kind of a different mass. And then that gives you a nice formalism to actually put this effect into the standard quantum formalisms that we're used to working with, and to predict, first of all, to come up with new schemes for how you can actually change the redshift on demand. Using multiple levels of the atom, you can actually tune how large the redshift effect is. But also then see how, if you put your atoms in a cavity, let's say, and have them all interact with each other where they're at different heights, how will the redshift start to interact with the all-to-all interactions that you get from the cavity, and how, for example, can entanglement start to appear in a system where you're also experiencing the redshift. And so this is now kind of a system where we're probing both entanglement, quantum entanglement, and relativistic effects at the same time, and starting to see them interact. So I'm running out of time, but I want to say we're really making experimental progress towards this. All these proposals I just mentioned are to see very, very small effects. And we still need to work on making these clocks better, basically. And so in June's group, there's very nice work that was published just 2 days ago in PRL, showing that they can now achieve coherence times of 2 minutes, and that they've reduced the stability by another factor of 2, which is another factor of 4 in averaging times. So this is really promising for being able to see these effects at the 10 to the minus 20 or below level. So now it's only 11 hours to average down to 10 to the minus 20. And in my group, we've also been trying to understand what limits all of this. What are the fundamental limits? I would say June's paper also touches on a lot of this. And we had a paper published last week in PRA where we actually experimentally measured the lifetime of the excited clock state in strontium. And June's paper also made a measurement of this, and I'm happy to say they agreed, even though we did them completely independently. And we also now see, even when we do kind of dynamical decoupling type like sequences, we can see coherence times that are on the same time scale as the lifetime of the excited clock state itself. We can now see atom-atom coherence times exceeding 160 seconds, which is really pretty remarkable. June's group is starting to do accelerometry type experiments, interferometry with the Wannier-Stark states. And they're really starting to explore how to get rid of these interaction effects that were limiting them before. They generated a superlattice to remove nearest neighbor sites, populations on nearest neighbor sites, so that now some of the interaction effects I mentioned before go away. And very exciting, they're also thinking about, given the number of atoms you have, and because we're actually really becoming limited by the density effects, how can you do better by making these spin squeeze states? This is a lot like what we heard yesterday about with the axion searches, where you use squeezed light. Here, you want to use spin squeeze states of these atoms to push beyond the kind of standard quantum limit. And remarkably, they're seeing quite a high degree of squeezing, and even starting to see metrologically relevant levels of squeezing, where you can really start to see clocks that are performing at the best levels of these clocks using these entangled states. And so in the future, we can really think about combining all of these things and having entangled states of clocks at different heights, and it's very exciting. I'll mention very quickly, I'm also working on a kind of different kind of test, and with Igor, we're trying to think about what this test would really imply, but where we directly test the Einstein equivalence principle by comparing these redshifts that we regularly measure to the special relativistic effect when you accelerate the clocks. So is it the same thing to accelerate 2 clocks versus for them to be in a gravitational potential? And we're really gearing up to do this experiment now. And then the last thing I'll mention is not funded under this program, but from the EPI, from Ted and Kathy. I have a complementary effort to try to basically go back to making these effects larger by kind of going back to the Pound-Rebka style experiment. And I was proud of doing a meter scale experiment. I felt like that was very ambitious, but then I followed Jason's talk where he's doing 10 meters, so this looks like nothing. But I'm very happy to say that last time I gave this talk at the EPI meeting, it was still a SolidWorks drawing. Now there's an actual cell phone drawing, or cell phone picture where we have the actual setup, and we're currently baking it out. So I'll thank you for your attention and your patience. I'm sorry for going slightly over, and take questions.
Good, thanks.